Hi, Bryn Swan here to discuss partial differential equations, specifically uh, numerical methods and their discretization and resulting stability. So, starting with one of the two main methods, the first is finite difference for spatial. We're going to be talking about spatial application here. So essentially, you want to transform a partial differential equation into a discrete problem. Specifically, the domain is broken into a collection of points or nodes. So again, points or nodes, and for first order, if you use a uniform breakup, you can look at it as a 5-point star. And here's a simple example, an equation that results from that finite difference. Second order can be used as well, and that expands upon this, and it looks at the nodes that are, it basically moves another order out, where the nodes adjacent to the other nodes, or actually points, are factored in. So, and this is an example of center difference. There can be forward and backward difference. So, fair number of options there. Now, for finite element method, the biggest difference here, I'm going to jump right to it, is the domain is broken into a collection of continuous elements, not discrete nodes. So again, the meshing looks similar, but the focus here is now on the element instead of just the node. So finite element basis functions use Lagrange polynomials to weight the influence on the element. So 1D representation can be seen here for a 2D set of elements. Kind of poorly drawn, but it essentially looks like a pyramid in graphical format. Partial differential equations, the generic formula is here. We've got, for engineering, we'll typically deal with elliptical or parabolic or hyperbolic, and each is handled slightly differently. Jumping in on how we'd apply these various functions in the temporal or time discretization, it's kind of pooled in three main groups. You've got implicit, which are unconditionally stable, explicit, which are conditionally stable, and the semi-implicit, which are stable. They don't have conditions. So the difference, really explicit, what's happening here is the condition is, put simply, that the element, the node, can't move farther in any one direction than its adjacent node in a time step. If it moves farther, then that no longer can be predicted by the bounding nodes. So in order to maintain stability, it has to move less than that distance. So that's time discretization and stability. I think that's it. Thanks.